All right, let's dive into some further mechanics. We're going to explore the direct link between force and momentum, and then we'll get into the really interesting physics behind what makes things go in circles.
First up, let's tackle the concept of impulse. It's a fundamental idea, and as you'll see, it's really just another way of looking at a change in momentum. Everything really kicks off with a classic, Newton's second law. You know this one. It simply states that the force acting on something is equal to its mass times its acceleration. That's our starting block.
And of course, what's acceleration? Well, it's just the change in velocity over a specific period of time. We write it as delta v, the change in velocity, divided by delta t, the time it took for that change to happen.
Okay, so here's where it gets interesting. When we combine those two ideas, we get something new and incredibly useful. If you take a force and multiply it by the time it's applied, that's what we call impulse. And it turns out that's exactly equal to the change in the object's momentum. So, simply put, impulse is change in momentum.
So now that we have this principle down, let's apply it to something a bit more complex. Think about what happens in two dimensions, like when two billiard balls collide and scatter across the table.
You know, the secret to not getting overwhelmed by these 2D problems is to just break them down. Instead of looking at the whole messy collision at once, we're going to analyze the motion along the horizontal x-axis and the vertical y-axis completely separately. The cool part is that momentum is conserved on each axis, all on its own.
So let's start with the x-axis. Before the hit, all the horizontal momentum comes from that first ball, m1, moving at velocity v1. After they collide, that initial momentum has to be shared. It equals the sum of the new horizontal momentum components of both balls. We use cosine here because we're looking for the part of their motion that's along that horizontal axis.
Now, for the y-axis, think about it. Before the collision, there was zero vertical motion, right? So the total momentum on the y-axis was zero. That means after the collision, the total y momentum still has to be zero. So whatever upward momentum one ball has, the other one has to have an equal and opposite downward momentum to cancel it out. That's why they sum to zero, and we use sine to find these vertical parts.
So what we're left with is basically a puzzle. We have two equations, one for the x-axis and one for the y, and two things we don't know, the final velocities. It's just a classic set of simultaneous equations. The process is pretty mechanical from here. You plug in the numbers you know, you manipulate the equations a bit to get rid of one of the unknowns, solve for the other one, and then plug that answer back in to find the first. And after all that algebra, here are our answers. See that little negative sign on the first ball's velocity? That's not a mistake. It's just telling us that after the collision, it actually bounced backward along the x-axis. And if you think about it, that makes perfect sense.
Okay, but here's the thing. Not all collisions are the same. A really important way we can tell them apart is by looking at what happens to the kinetic energy, the energy of motion.
We basically have two main types. In what we call a perfect elastic collision, like our ideal billiard balls, both momentum and kinetic energy are conserved. Nothing is lost. But in an inelastic collision, say a car crash, momentum is still conserved, but a whole bunch of that kinetic energy gets turned into other things, like heat from the crunching metal or the loud sound of the impact. And while we're on the topic, there's a really handy little formula that connects kinetic energy directly to momentum. An object's kinetic energy is just its momentum squared divided by twice its mass. It's a very neat relationship.
And you might ask where that formula comes from. Well, it's actually pretty easy to derive. You just start with the definition of momentum, P equals mv, and solve it for v. Then you plug that into the standard kinetic energy formula, 1/2 mv squared, do a little bit of algebraic cleanup, and there you have it.
All right, for our last section, let's completely shift gears. We're moving away from things hitting each other in a straight line and into the fascinating physics of what happens when something goes around in a circle.
Now, when we talk about circular motion, we usually ditch degrees and use a different unit called the radian. It sounds complicated, but it's not. 1 radian is just the angle you get when the arc of the circle you're looking at is the exact same length as the radius. The main thing to remember is that a full circle, 360 degrees, is just 2 pi radians.
And that leads us to angular velocity, which we write with the Greek letter omega. It's basically a measure of how fast something is spinning, how much angle it covers in a certain amount of time. You can find it by dividing the object's regular speed by the circle's radius, or by using the time it takes to go all the way around once.
Now here's a really crucial idea. An object moving in a circle is always accelerating. You might think, but its speed is constant. And that's true, but its direction is constantly changing. And since velocity includes direction, the velocity is changing, which means it's accelerating. By using a little geometry, we can actually derive the formula for this special kind of acceleration, called centripetal acceleration.
And you know the rule from Newton's second law. If there's an acceleration, there has to be a force causing it. In this case, that's the centripetal force. It's the force that's always pulling the object in, towards the center of the circle, keeping it from flying off in a straight line. It's just the mass of the object times that centripetal acceleration we just talked about. So let's end with a thought. If this centripetal force is always pulling towards the center of the circle, but the object is always moving along the edge of the circle, well, that means the force and the direction of motion are always perpendicular to each other. So what does that tell you about the amount of work being done by that centripetal force? It's a key question that really ties these ideas together.